goes in this path, and this is many times this, you have an amplifier. This guy's small current flow affects this guy's large current flow. And what an amplifier really is not so much something that produces power, but regulates power. It basically lets a small voltage or a small current make a larger voltage or a larger current result from it. So if you start putting in small signals like this, you can get some pretty big signals coming out the other end. And that's why the transistor is so useful. It's a basic amplifier. But we use them in computers too, so it's more than an amplifier. It could also be a switch. How is that possible? More pictures coming up. I think when you read all these questions on transistors in test questions you might encounter on the general or extra test, you'll appreciate what it is about the transistor that makes it work, because it's not that mysterious. It's just a matter of understanding it by having it explained to you. My gripe is the book doesn't do a very good job of that, so I'm here to make up for that. Let's just, for the sake of illustration, draw a graph of what a transistor is going for inside. All right, now let me draw a real circuit here. You're generally going to find a transistor circuit looks like this. You're going to feed DC voltage, let's say 12 volts. Between here and here. And you can use a capacitor to couple in your signal so that the AC components will go through and the DC components will be blocked. And what's going to happen normally is you're going to get some current to flow here, and some current to flow here, and some current to flow here, and some current to flow here. And those values of those resistors, R1, R2, RL, because that's what I will describe as the load resistor, and RE, which is the emitter resistor, are designed so that when you have a transistor, whatever value of current flowing through this collector to emitter path, remember this is the base, will fall on this straight line. What's the straight line representing? It doesn't matter which axis I call which, just arbitrarily and capriciously, I'm going to call this one voltage. I'm going to call this one current. And if I didn't put any current through this path, if this guy were just cut off for some reason, you would have no current flow, no collector to emitter current flowing here, if you had no base to emitter current flowing here. If you have no current, then all the 12 volts here will drop across the collector to emitter path. So where is that on the load line? Well, it'll be right here. You would have, whoops, excuse me, I'll be right here. You'd have a case where the current is 0 and the voltage is maximum. That position is called cutoff. Why? Because nothing's flowing through the transistor. If I'm not injecting any minority carriers in the base, I'm not going to get any flow of current from collector to emitter. And this transistor is like a switch. It will be shut off. Nothing will come out. Okay, what if I go the total other direction? I up the current here, and the voltage starts to drop across the collector emitter junction. So more current flows here, more current flows here as a result. In fact, the ratio of the change of current from collector to emitter based on the change, it's really the change, not so much the actual from base to emitter, as the name, it's the so-called beta. It's the amplification factor. How much this output changes relative to this path here, how much this path is affected by this path, is really where your gain comes from. That's your amplification factor. So let's say I keep feeding more current in here until, essentially you move from here and the voltage across here starts to drop because the current's going up, and finally it hits a point where at the voltage I've given this thing, the voltage here is zero. I mean, basically this thing is wide open. If I feed more current in, it's not going to go any, the voltage can't get any lower. You really hit a rail here. This thing is called saturation. Now, I could have easily flipped it around because you think of cutoff at the bottom and saturation at the top. But what's the difference? As I said, it was arbitrary. Which axis I called voltage, which one I called current. The fact is, if you've got current flowing and no voltage across here, you're saturated. This thing cannot get any lower than zero. And if you got no current flowing in there and all voltage and no current, you're cut off. This thing's not operating. In between, you're going to run up and down this load line. And that's what this thing is called, a load line. That is based on the load resistance here. In other conditions, is going to be the slope of that line. And what's going to happen is, if I put a signal in here and I get an amplified signal out here, what's really happening is I'm sort of in the middle and I just go this way and I go this way, up and down the load line. Hopefully not hitting cutoff and not hitting saturation, because as soon as I do, what's going to happen is I'm going to start hitting that point of saturation or cutoff where I can't go any further because I hit this, either this rail or this rail, and I'm going to get distortion because what should have been a signal like this instead is a signal that's more like a square wave. Okay? So if you want linearity, if you want what comes in and what goes out to look the same, you have to stay within these boundaries. If I put no signal in, I should be right here in the middle. They call this thing the quiescent point. Now this is a particular configuration called a Class A amplifier. And because of the way this guy's down here, it's called a common emitter. Meaning your ground reference is really attached to the emitter. If I flipped it over, it would be what's called an emitter follower or a common collector. And if I put the base on the bottom, which you can, you get a third configuration, common base. Common base is used for voltage amplifying. Common collector or emitter follower is used for current amplifying. And if you use common emitter, you get both. You get power amplification. It boosts the current and the voltage pretty equally. So you've heard of a grounded grid linear amplifier. Maybe if you read the books, you'll run across that. That's a kind of a common base concept where you're looking more for voltage amplification, not so much power. Even though it's supposed to be a power amplifier, it works better that way because it doesn't saturate very easily. That's the transistor lesson here. This is how they work. This is what they look like. And these guys here are your bias network. That is your resistors that set up a condition so that you'll be roughly here when there's no signal coming in. And then you can slide up and down the load line when the AC, the signal you're trying to amplify shows up. If you just want to use it as a switch, well, that's not the way you configure it. You would basically probably not have this resistor here. This thing would be clamped off except when a signal shows up to make it turn on. And transistors are used as switches very often. In computers, all the time. That's basically what they do. We'll get to that subject. We're about 1 hour into a 2-hour presentation, so I think the timing is working out pretty well.
Good.
All right, if we use a transistor as a switch, sometimes the symbology, since a lot of transistors all over the map would be difficult to, look at on a schematic. It'd be hard to figure out, okay, how do I make sense out of this? So we've come up with some shorthand things, and they look like this. And sometimes we do a little additional thing, like one of these buttons on the end of it. Each one has a purpose. What these guys are logic. Let's just say gates. They are nuts and bolts of a computer, or any control circuit for that matter. They make decisions, they do computations, they do timings, they do a whole host of things that computers rely on. And we're going to talk about that. But first, before we do that, we have to talk about what logic is. When we talk about logic, we're not talking about analog, we're talking about something called digital. These are in the digital realm. In an analog realm, I'm looking at signals that vary all over the map between some maximum positive and some maximum minimum, some maximum negative value. In the digital world, I'm either going to be at 0 or I'm going to be at some positive value. And nothing, well, I'll be at some other value. I'll be at two levels. It may not even be 0. One could be plus 12 volts, one could be minus 12 volts. And indeed, that actually happens in a framework called RS-232. You may have heard of that in the old days as one of those interfaces used to put your serial device on your computer. And you deal with things like baud rates and parity, and whether you use a 25-pin connector, which only had 3 active pins, by the way, or the newer one, the 9-pin connector. In addition to the 3 active pins, the other pins were defined as things like clear to send, request to send, besides the 3 basic ones that were transmit, receive, and the common return. But the others were used to regulate traffic flow. Flow control was important because you may have had a circuit where only one guy can talk at a time, so you had to give the sender the go-ahead signal to send and not send when he shouldn't. Or, in the case of your printer, if you took it offline, you don't want the data flowing into the bit bucket. You wanted the computer to know, whoops, hey, I lost my serial device out there, so don't send anything until I get the go-ahead. Those were control lines that were attached to the other 25 pins of the other 9 pins, depending on whether you had a DB9 or DB25 connector. Point is, it was all digital. You had 2 levels, whether it was minus 12, plus 12, or in most logic circuits, plus 5 seems to be popular, and 0. That's the so-called TTL levels. Transistor logic made its debut about 1967, I remember when it happened. I was an intern at Motorola. And we were setting up those devices before there was diode transistor logic, and I don't remember if there's anything before that. Anyway, this is the binary world. You're either here or you're there, and I sort of alluded to why that is earlier, because the devices themselves that keep this information flowing include the transistor, which can be on the load line at saturation or cutoff, or whichever, one end or the other of the load line. So you've only got two binary conditions, a 1 and a 0 condition, whichever one you pick to be arbitrarily the 1 and the 0. In the days when we used to store information in a magnetic donut, there were two wires called X and Y, which when there was enough current going through, it would actually cause the magnetization to change from going clockwise to maybe going counterclockwise. And the sense line that went through it that would determine which way that was. It would have to do it destructively, by the way. It would have to actually reprogram that donut and get a different voltage blip if it was already programmed the way you were trying to program it, versus if it was programmed in the opposite sense. They called it the destructive read-write-restore cycle, but it took 650 nanoseconds to do that. And nowadays, a modern, the random access memory chips that you normally buy do it in nanoseconds, usually less than 200 nanoseconds, maybe a lot faster than that now. So the old-fashioned magnetic core memory is long gone. There's another example or two. There's a switch. In the classic sense, it's either open or it's closed.